I'm going to be talking to you today about learning from data. So I'm a statistician in the School of Maths and Stats. Statistician slash data scientist, I guess, for various definitions of data science. And I teach the second semester unit data 2002, which is called Data Analytics: Learning from Data. So a pretty horrible name. I really don't like the colon, but the idea of the unit is interesting to me in that you want to be able to take some data and do some interesting things with it, derive insights from it, and come to conclusions and recommendations. And so a lot of the statistical methodology that I develop is very closely tied to this idea of actually being useful and generating things for other people to be able to apply or use or find features in their data. So, talk about a few things today. I apologize to the vegetarians in the audience. This is very much focused on red meat, in particular cows. So I'll talk a little bit about my collaboration with the red meat industry. A few examples in animal welfare space before we get into the core problem, which is predicting eating quality. So how well is a particular sample of beef going to be received by the consumer? And I'll tie that in with a recent paper on regularized learning. And so I won't assume too much. How many people in the audience at first year? Okay, all right, so like a third. So yeah, I do go back and add a few things that hopefully you don't get totally lost in what we do, and I won't go too much into the details, so it should be fairly accessible. All right, so maybe I should take a step back and talk a little bit about myself. It always helps, I think, to sort of understand where people are coming from. I grew up in a small country town, or a farm outside of a small country town in New South Wales. It's called Griffith. Does anyone know where Griffith is? All right, I'll show you. So it sits sort of here in the middle of your big, generous middle of nowhere, right? So it's here, and the specific place that I grew up, so there's the town, and then you go out from the town past a smaller town here called Tarr. And yeah, my home, for some reason, it gets its own name. So there's actually a farm called Brendan, and it's maybe it's just because Google Maps knows a bit about me, but I don't know if everyone else's, but it gets an icon. So anyway, that's where I grew up. So I went to school there, primary school and high school out there, then I went to the University of Sydney, and I did a double degree because of course I had no idea what I wanted to do. So I did a science degree, a commerce degree, and in my commerce degree I ended up doing a bit of what's called econometrics, which I guess is now an arts degree in economics. And in the science I did statistics or financial maths and stats. So then I did honors, and then I did a PhD, and sort of these things kind of just happen sequentially. Right? There was no real thought process behind it. It just happens that I enjoyed doing what I was doing and kept doing it, right? And then I went and did a postdoc at ANU for a while, and then I was at the University of Newcastle for a couple of years, and then I've been back to Sydney since 2018. Anyway, so that's sort of my brief life history. What do I do? What do I want to do? I want to develop methods that help scientists do better science. If you want to put up just a short take-home message of what I try to do, that's basically what I do. I also get my hands dirty in the sense that I get involved and actually do the data analysis myself as well with some select colleagues, not with everyone because there's just a very long amount of demand, so you've got to pick and choose what you're actually getting into. Okay, so the set of colleagues that I work very closely with, these people from the red meat industry, and they're from an organization Livestock Australia, but also from different universities around Australia and around the world as well. So here's what we work on. We work on mostly sheep and cows, definitely no pigs. They're evil. It's not as evil as chickens. Right? So chicken is the enemy, and what we're trying to do when we're developing these tools with the marine industry is develop a way of guaranteeing a particular consumer eating quality experience. Right? You buy chicken, and it's the same bland taste every time. Right? It's not that repeatability; it's repeatedly boring. You buy beef. And sometimes it's awesome, and sometimes it's not so good. So we want to sort of take the guesswork out of buying sheep and beef. Okay, so the industry partner that I work with in Livestock Australia, the specific program within Livestock Australia that I work with is Meat Standards Australia, MSA. So they're interested in things like animal welfare, new technologies for evaluating carcasses and live animals. They provide a lot of business intelligence to producers, so the people that grow the animals, abattoirs, the people that kill the animals, and users like Coles and Woolworths, right? So that they know a little bit more about the supply chain, and their core product, I guess, is this eating quality prediction model. So why do they want to work with me? So my experience is in robust statistical methods, so developing techniques that work well even when you might have outliers in your data that might corrupt standard methods in some ways. You can apply robust techniques to try to limit the impact of those outlying observations. I do work in feature selection, so identifying which variables are actually useful and which variables are not so useful, or which predictors, which things that you can measure are actually useful. Modeling and building dashboards and visualizations and things like that. So I have a particular skill set that they find fairly useful. All right, a couple of short vignettes on a few projects that we've worked on recently. This was one with a PhD student a couple of years back now. She was working on taking infrared camera measurements of the carcasses, both when they were on the farm, or they were carcasses when they were on the farm. They were animals, hopefully happy live animals. So basically what would happen is the animal would walk through the race or the corridor, and then this camera would film it, and we'd try to get a reading of what is the body temperature of the animal. In particular, we're after the eye, right? So the eye temp was what we were trying to get a handle on. Of course, that's hard in a human that's sort of sitting in front of you with their eyes open. It's even harder if you've got an animal that's throwing his head around, is blinking, doesn't be photographed. So you get this sort of series of data out of it. It looks something like this, right? And you can identify different times where maybe the eye was in view of the camera, maybe where just the body was in view of the camera, something weird was going on, so it just took a bit down. And of course, there's always spikes and weird stuff that happens in this sort of data. So Holly, the PhD student, she painstakingly went through and identified when these features, when these things are happening. So when we had a good view of the eye in the shot, when maybe the body was in the shot, maybe the animal wasn't in there at all. And so she went through and then summarized that data and worked out, okay, how can we do something a little bit easier, a little bit more automated, like what features should we extract from this series of data? And then once we did that, of course we need to map it to actual outcomes. So whether or not the carcass when it died was compliant with various standards, whether there was any relationship with air quality, these sorts of things. So that's one project. Another one more recently was with Cassius, and he was looking at the ability to detect whether a particular organ had a defect in it. So at the moment what happens is a vet, like someone who spends 6 years training to be a vet, basically has to come in and assess each of these organs to see whether they've got some sort of ailment, right? So whether it's diseased or healthy, which is not a very satisfying job for a human. It's also very expensive, so that's charged a lot of money. So what we wanted to do was to see whether if we put it through what is essentially a baggage scanner from the airport, so a CT machine. There's a company called Rapiscan that makes these devices, and they're looking for other ways to use these devices or other places that they can sell their machines to. If we take this hyperspectral imaging of the offal, the organ, can we distinguish between diseased and non-diseased samples? So again, this kind of seems fairly straightforward, but the data, well, you need to do some local smoothing, some averaging. We ended up analyzing the first derivative of the series as well to think about differences in shift or locations, so we get rid of those sorts of things. And then apply things, machine learning type tools like random forests and partially square discriminant analysis to try to differentiate between healthy and diseased different kinds of organs. Okay. And then even more recently, looking at shade and shelter. So again, this is sort of in the animal welfare side of things. So if you put your animals under a shade structure, are they happier? Are they less stressed in some sense? And do they have better eating quality outcomes or better compliance outcomes? So are they better carcasses down the end? So this is kind of a fairly straightforward question, right? You've got animals that are in a feedlot that are just under open skies. You've got animals that are in a feedlot that have a shade block over them, and then you've got animals that have like a proper structure over them. And so in some sense you've got three trend groups, and you can just look and see other differences between the three trend groups. The more interesting part of the experiment is that we had these internal body temperature measurers inside the animals, and they were taking 10-minute measurements of the body temperature for like 90 days, 100 days, and there were 90 or 180 animals that we did this for. Right? So we've got this kind of amazing time series data measured in fairly granular increments across quite a long period of time, and that lets you do potentially much more fancy things. But it might not be that the shaded animals get as hot during the day, and they might get not as hot during the night, or relative to the animals that were unshaded. And you can also maybe think about, like in this picture, identifying where they go on taking a drink, right? Because when a cow goes to the trough and takes a drink, they're not just taking a sip, they're probably taking in like 20 liters or something of water, and that's reflected in the internal body temperature measurements that have this dip, because that's where the measuring device is in one of their stomachs, I think. So when they take a drink, the body temperature goes down. Okay, so that's a little bit on small projects. I'll now move to like the actual core, which is eating quality. So it kind of probably seems a little bit bizarre to be wanting to predict the eating quality of cows, right? But what it lets the industry do is breed towards a tastier product over an extended period of time. If they have this phenotype that they can predict, they can identify which cows make tastier offspring and which bulls contribute to that. but they can also, at the abattoir, think about product differentiation. So they can segregate out the different muscles and sell them at different price points, basically. So this underpins branding strategies. If you go to Coles or Woolworths or Harris Farm or whatever, then you've got premium brands, and then you've got sort of average brands, right? So this sort of prediction model underpins that, well, it gives some science to that process rather than just saying these animals came off this farm, therefore they should be tasting it. Okay, so this has been going on for like 20 years, maybe 25 years now. So there have been like more than 1 million samples have been eaten from consumers in Australia and Poland and South Africa and America and Japan, Ireland, UK, Wales, France. So there's a whole bunch of countries that run these sorts of experiments, and we have this massive amount of data that we can try to use to develop an inequality prediction model. So at the core, we have real consumers, right? We don't have trained panelists, like taste panelists. We have the data that we're observing is the actual consumer that would be sitting down and buying a product and looking at the data, right? So what does this do? Why do they collect this data? I sort of mentioned it, it helps inform this inequality prediction model, and because of that differentiated pricing strategy, the economists have estimated that it generates about $200 million extra a year for producers, right? So there's actually value here in having this inequality prediction model. So this is sort of what happens. This is a fairly old picture. But basically, you've got people that come in and sit down. They've got palate cleansers and water, and they're given a piece of paper, and on that piece of paper is a couple of lines, and they have to assess each sample, and they eat 7 samples in a sitting. So they assess each of these samples, and they give it a rating, and that sort of generates the data for us. Okay, so what do they rate? They rate the product in terms of its tenderness, juiciness, flavor, and overall liking. Right? So there's 4 different lines, and on the line from like 0 to 100, they make a mark where they think what this product tastes like in terms of these different factors. So typically, what you see is that there's a lot of correlation, a lot of similarity between tenderness and juiciness. If you like something, you might not really be able to differentiate is it the juiciness or is it the flavor that's coming out. So these traits are super highly correlated. And what we end up doing in terms of our raw inequality prediction model is sort of averaging over these 4 traits to get this MQ4, inequality 4 score. So we say that predicting inequality is essentially equivalent to predicting this MQ4 score, some weighted average of tenderness, juiciness, flavor, and overall. Okay, so that's our target variable. That's what we're trying to predict. How do we do it, or what do we do it for? We do it for each muscle, each muscle that is commercially relevant, so about 70 different muscles, and for a variety of cooking methods as well, right? So you might grill, so have barbecue, you might roast it, or slow cook, or stir fry, or shabu shabu, or like meat used to be. We did some work with briskets recently as well, right? So there's a whole bunch of different cooking protocols for different muscles, and we have an inequality prediction model for each muscle cook combination. So there's about 300 different submodels in total. So it's not just one overall model. We've got like a precision data science for predicting how each muscle cooked in a particular way will taste to a consumer on average. Okay, So the model takes this sort of form. It's got some intercept value, so some sort of baseline value for each couple combination. And then it's some function of like the marbling, the sex, pH, the feed type. HGP is hormone growth hormone, so it was fed these hormones to make it grow faster. Pump height, maturity, carcass rate, the hanging method, so how it hangs in the abattoir and then a day's aging, so how long past slaughter do you age the product for, which can help eating quality. So that kind of seems fairly straightforward. Right? We've got a bunch of these different predictors. Some of them we measure on the carcass at the abattoir. Some of them we know because of the way that the animal was brought up, like what it was fed, whether it was grass-fed or grain-fed, right? And some of them we can predict out too. So we can assume that this animal or this sample is going to be eaten at 5 days, or 10 days age, or 20 days age. Right? So all of these things we can potentially just put into a model. Unfortunately, it's not that straightforward. So what meat scientists tend to do is they tend to really like getting strip loin samples. So we have a huge number of strip loin samples relative to the other muscles. So we have this imbalance in our data when it comes to which muscles tend to get sampled. And this is partly a function of the way that the data is collected, right? So it's collected from various experiments that are probably targeting different things over time. And for each experiment, they kind of want that baseline muscle, that strip loin sample, so that they can compare with other experiments. So basically, every experiment runs gets a strip loin, and then we try to opportunistically sort of collect other muscles and improve them as well, different ones from time to time. We also have a lot of grilled samples. So we have a lot of grilled strip loins. So if we were trying to estimate an inequality prediction model for grilled strip loins, we can do really well, right? But there's a bunch of other cooks, right? Roast and stir fry, that's a bar that they've got a fair number of samples on, and then there's some others that we have very, very few samples on. Okay, so we've got a lot of grilled strip loins, but we're trying to estimate three different models, not just the grilled strip loin model. And then you can kind of imagine that when you're looking at data on one particular sub-sample, like the sous rumps or something, you might not have a lot of variation in the covariates for that particular class of muscle, right? So, in particular, hang type, almost all abattoirs in Australia use one-handed hang type, so that's how it is hung up at the abattoir. Sometimes you just might not have any animals in a particular class, muscle combination that are treated with hormone growth hormones. So we might not have variation in the other covariates, so we might not observe different aging points for many of these muscle combinations. So there's a few challenges, which means that we can't just stack all this data together, pretend that we have just a linear model, which I know doesn't make any sense to about validity, because you won't get it. But a standard approach is right. We can't just put all these covariates into one model and say, give me my estimates for this model we're trying to build. Okay, so how do we get around this? We need to make some assumptions, basically. So we need to build up our knowledge, borrowing strength from similar muscle combinations. So for similar muscles, we're going to assume that they're basically the same in some way, and for similar cooking methods, we'll assume that they're the same in some way, so we can start to pool data over these different combinations of muscles and cooks. And this, at the moment, is done in a fairly manual sort of way, where where we build up effectively a table of coefficients and we sort of smooth those coefficients over similar muscle input combinations. We also want to enforce scientific truths and empirical observations, right? So things that we know a lot about, we want to make sure that they're reflected in the coefficients. So as the animal gets older, for example, that should result in a decrease in inequality after a certain threshold. As you have more marbling type of products, then that tends to increase inequality. If you increase the number of days that you age the product for, that should also increase. So these coefficients should have a known sign up to a certain point. If you go past a certain point, then inequality goes down with days aged, and hormone growth hormone typically decreases inequality. So we want to be able to enforce these sorts of things as well. And then within each of the predictors that we're using, some of them are categorical, others are continuous. So the marbling score that we use is a continuous variable measured between 100 and 1,190 in 10-point increments. And a human does this, right? So there are guides that they assess each carcass relative to a particular set of images, and they come up with a marbling score for the animal. But it might not necessarily be the case that the difference between 100 and 200 marbling points is the same as the difference between 1,000 and 1,100, right? So you want to think about maybe we need to transform the data in some way so that we can account for non-linearity in the relationship between inequality and these variables. Okay, so the goal is to avoid this sort of more manual and tedious approach to model building, where we don't have to estimate like 300 different models and then smooth coefficients and pull different groups of data together in a manual way. So sitting there just estimating hundreds of different submodels, that would drive you nuts. We want to borrow strength from different classes, so acknowledge that some muscles are similar and some cookie methods are similar. And we want to also be able to let the domain experts, the meat scientists, contribute their knowledge, right? So this is definitely very much the data science end of the spectrum, where you're bringing in experts with their understanding of the problem as well as the data. Okay, so we'll get a little bit more mathematical now and talk about what these models look like and one way that we've sort of gone about trying to tackle this problem. We're going to say we have an outcome variable y and say an observation. So I'm just going to set up a very basic linear model here. We've got a vector of predictors, which are our x's, so these are things like malware, whether or not it has HTTP, days age, those sorts of things go in your x vector. And then the impact of those predictors is described through this coefficient vector beta, right? So the marbling will have a particular coefficient, and that sort of describes when the marbling changes how much will your y change, or the inequality outcome change. So we could write this down as y equals x transpose beta, and we could take an input, an example vector of inputs x, and try to predict what the inequality outcome will be y by putting it into this linear model. So, of course, we need to find that true, well, we've got that true primary vector beta. We need to find an estimate of it, which is why it's got a hat down here. So this is beta hat, our estimated coefficient vector, and we need to be able to estimate that somehow. And the way that that's typically done is by considering the residuals, right? The differences between our observed values and the values that our model would predict, and we want to minimize those discrepancies in some way. Okay, so this is the slide that I put in like an hour ago, just in case. That might have been a bit fast, but this is really, really important. So if you don't understand this step, then the next 10 minutes is go to sleep. So we've got a model, so it looks like this in perhaps the general form, right? Going to bring that right back down to just a simple linear regression model where you've got your outcome y on the y-axis, so inequality on the y-axis, and your outcome x on the x-axis, and that might be the market score, right? So we've got these observations, the little x's, and we're trying to find this line that goes through this data cloud in some really good way. And then there's the intercept theta naught, and then your beta 1 is how we estimate y to react in response to a change in x, a one-unit change in x. And so then how we try to find this beta hat, beta 1 hat, I guess in this case, this estimated slave coefficient, and intercept beta naught hat, is by considering these vertical distances, these residuals. Right? So we try to minimize the sum of squared residuals actually, but it doesn't necessarily have to be that. But that's how we try to come up with this good line, this line that fits the data in some way. So these vertical differences, the differences between this value here would be what we observed for this observation, the y value that we observed for this observation. And then down here, this would be the value over here that we would predict for this observation given our equation. Is that okay? All right. Okay, so how do we find these beta hats? I talked a little bit about it. In the classical setup, you would be setting up some objective function, like the sum of the squared residuals, and trying to minimize that. And that's fairly straightforward. There's a nice closed form solution to do that. What regularization or regularized learning does is thinks about imposing some additional constraints on this minimization problem, right? So rather than just minimizing the residual sum of squares, this component here, we add in some penalty term, which I've left deliberately ambiguous here, because we could take very many forms, and maybe some tuning parameter lambda that sort of describes how much penalization would you like to impose on this minimization problem. Okay, so I'm going to start very briefly with one of the more common kinds of penalties. And so here we've got the residual sum of squares again. We've got our lambda, our tuning parameter value that determines how much regularization we'd like to impose. And then this is the particular kind of penalty that gets marketed as the lasso, but it's just an L1 penalty term, right? So the sum of the absolute values of the coefficients. So this does two things. It tries to shrink or put some constraints on the size of the estimated coefficients. And a sort of almost a byproduct of that as well is the geometry of this objective function is that it actually does variable selection too. So this is a picture that I saw from Rajan, who gave a talk kind of like this a little while ago. In this special case, where we've got two predictors, x1 and x2, and their coefficients beta 1 and beta 2. This is what the setup might look like. This point here would be the unconstrained solution, right? So if you didn't have any penalty, and you just were minimizing the residual sum of squares, you might come up with this value for beta 1 and that value for beta 2. When we want to impose this additional penalty, we can write the minimization problem as just a constrained minimization problem. So we're still minimizing or trying to minimize the residual sum of squares, subject to a constraint on the sum of the absolute values of the coefficients, right? And so geometrically, this is what that looks like. We've got now this absolute value constraint here, and we're trying to find where we would estimate these coefficients to be subject to that constraint, right? So we can't estimate anything outside the diamond here, so this is not feasible anymore. So we come to sort of the closest point on that diamond, which happens in this case to be when beta 1 is equal to 0, right? So it's doing feature selection because the constraint has these sharp edges, these vertices, and at the vertices, that's where we estimate one of the coefficients to be exactly 0. Okay, so this thing that they've called the lasso, it wasn't the first time that an L1 penalty was added to a residual sum of squares. They just did it in a really well publicized way, and then this got picked up and now has 50,000 or more citations on Google Scholar, and it's a very, very common, very popular way to try to shrink your coefficients and your variable selection at the same time. And there's heaps of different spin-offs from this, right? There's the pliable lasso, there's the group lasso, there's something called elastic net, which does a couple of different kinds of, not just L1, but also L2 regularization. There's the generalized lasso. So there's a whole bunch of different kinds of ways of adapting this idea of penalizing the residual sum of squares to get some, to emphasize the features in your case, like a group will see that these kinds of things. And so the particular client that we've picked up or adapted for use in this multiclass setting is a version of the fused lasso. And this looks a little bit scary, but it's really not that bad. You're basically just taking all your different muscle pull combinations. So you've got a data set for your build strip lines, right? You've got a data set for your roast strip lines. You've got a data set for your CV strip lines. You've got a data set for your roast tender lines. You've got a data set for your roast rumps. You've got a data set for your, keep going, but you get the point, right? There's all these bunch of data sets, and basically what we're going to do is refer to them with a superscript n for each, for the 1 to capital N. So this is potentially over the 300 different muscle combinations. And we've got these linear model for each muscle combination. Then we could think about taking all those coefficient vectors and kind of stacking them on top of one another, and that's what this is doing. So we're just stacking all these different data sets on top of one another, and we could try to estimate that stacked coefficient vector by, this is a residual sum of squares here. So again, we're still minimizing this residual sum of squares. And then we've got this kind of funky looking constraint here, or penalty term rather, where we've got something that involves the jth coefficients from the m and the n prime classes, right? So we've got this penalty term that involves the absolute value of these coefficients between classes. And I guess the key point here is that the j is kind of constant, right? So if we're thinking about this in terms of the inequality prediction problem, this might be the coefficient from marbling from roast strip lines, and this might be the coefficient from marbling from grilled strip lines, right? Two different classes, but we're trying to say that we want to put a penalty on how far apart these coefficients are. So it's got a sense of flavor as just a regular lasso, right? Absolute value penalty. But now we're thinking about the absolute value of the difference between coefficients for the same predictor between different muscle pull combinations. This is a way of trying to encourage different muscle pull combinations to have the same or at least a similar response to that predictor. Okay, so the way that we do this, there's a what's known as like a path algorithm that will actually go for for you. So the technical details are kind of worked out, but they're sort of fairly straightforward to apply this. You can kind of see the two special cases here. When lambda is equal to 0, we end up with effectively a separate least squares estimator for each muscle combination. So you let each class have its own individual model where you're not really worried about enforcing similarity between the combinations. When lambda gets really, really big, this component, this penalty, plays a huge role and actually enforces all muscle group combinations to have the same coefficient for each predictor, right? So every muscle group combination will have the same coefficient for modeling. Every muscle group combination will have the same coefficient for hormone growth hormone, right? So it's kind of like a pooled least squares estimator where you're enforcing or you're ignoring the muscle group combination that it came from. Okay, so to take a little bit of a step back, this is just an artificial example where we've got 4 classes. Class 1 and 3 were generated knowing that the true coefficient for those was 2, and class 2 and 4 were generated knowing that the true estimated coefficient for the true parameter was 1, right? So you can kind of see the evolution of these estimated coefficients for different values of the penalty parameter. So starting here, you've got effectively a separate least square solution where you estimate each of the 4 classes effectively individually, and they're allowed to have whatever estimated coefficient they'd like. And then as the tuning parameter gets larger, it starts to encourage these lines, the lines of similar classes, to snap together. And they snap together because of the L1 penalty, right? For the same reason that the lasso does variable selection, because of the geometry of the minimization problem. When these paths join, they join exactly, right? So you actually end up with the exact same coefficient estimated for classes 1 and 3 here, and again 2 and 4, and then at some point the penalty becomes too strong, and you end up with a situation where they're all forced to have the same coefficient, which is not a good outcome for either of the classes, right? Any of the classes. Okay. So here's the particular inequality data, and so there are 14 classes here now, so these are different muscle and pool combinations, and you can kind of see that it does a few nice things. It does some shrinkage, so it brings in the coefficients and makes the wild ones perhaps a bit less wild, which is probably a good thing. And then at some point, some of these start to snap together, which simplifies the problem, which is kind of nice. So it sort of does this grouping for us, and says that these muscle combinations should have the same coefficient for different variables here. The U and B is the marble variable actually. So at a particular point from the solution path, you could end up with a much simpler model than at either extreme. Okay. Of course, it's not so straightforward as to what value of lambda is a good one here. So you've got, from the totally separate least square solution through to the pools, somewhere in the middle is probably good. Where in the middle, and how do you do that? There's 2 standard approaches, which if you go on to do data 2002, you'll learn. Actually, no, we don't do. Talk about the information criteria in 2002, maybe 2902, but yeah, anyway, we might talk about it a little bit. So this is kind of like a measure of, yeah, we do, yeah, because we have exam questions on that. So this is a measure of like fit, right? So this is your residual variance, and when you include more and more predictors, your residual variance is only ever going to get smaller. So we offset that by some factor that involves the number of parameters in the model, right? So this is kind of like a trade-off between having more parameters, more flexible models, and the variance of the residuals, so how good a fit can we end up getting. And then the other approach is cross-validation, which we'll also learn about in Data 2002, when you hold out different sets of data and think about training your data on some subset, and then using that model to predict the holdout sample, and you do that iteratively, and using all of your data in a training and testing sequence. So I won't go into that. So I'm standing between you and pizza. Is it out there yet?
The pizza's delayed by 5 minutes.
By 5 minutes? Oh, excellent. Sorry, I can go for another hour if we need to. So just to summarize the multi-class modeling stuff, so it's nice in that it's a data-driven way to model what is a fairly complex scenario, and it makes it, I guess, more reproducible, right? Rather than trying to think about doing this bespoke modeling process, thinking about subsetting different clusters of data together and estimating submodels for each of those different clusters. In the paper, if you're interested in closed form, at least as good as the current approach, where we're looking at pooled or separate or manually adjusted. One of the challenges is that we can't actually just throw in, and you'll see here, we didn't put in all 300 different classes, right? So we put in 14. This was for one particular cooking method, a bunch of classes for one particular cooking method. At the moment, when we try to extend that, it turns out that there's just too much variation and it sort of falls over, right? So you can only really do this for different sort of already kind of similar methods, but that's okay. That's still a step forward where we can do a disparate cooking method combination, for example, and do it just a few times. Okay, so where might this go next? There might be the concept of outline classes, which classes that behave differently to everyone else, including the pretty early that modeling process. How do we identify those outline classes? We might want to include interactions between these predictors. So there's an interaction between like marking and naming, for example, which would be done in the bespoke process. There's no currently built into this process. At the moment, we've only done this for Australia. We've been building inequality models for other parts of the world where they're interested in these things, either with LAM. And there's been a big push recently, like I mentioned, that humans grade the carcasses, right? So they're looking at the eye muscle in the abattoir, which is sort of what's going on here. So a human would come along and look at this surface here and give it a marbling score. Ideally, we wouldn't rely on humans, like not that humans aren't good, but perhaps the machine is better in the sense that it's more repeatable, and it can actually have sort of the same device or build a very similar device and have a different abattoirs across the country, whereas we can't clone humans yet and have the same human look at product across the country. So there are these devices out there, and we're trying to get them accredited to do a good job of actually observing marbling and the different traits. CT scanning or DEXA would also be nice if you could just feed a carcass into a very large airport luggage scanner and have an output variety of measures of age of the carcass and how much fat was in it, that sort of stuff. That would be super nice, and they're working on that. And a bunch of work's going into identifying gene markers for identifying which genes are going to actually be tasted in the product. things that I'm interested in. Stability selection, so would you get the same answer if your data set was a little bit differently? Talk about outlying classes, robust feature selection and genetics data, and also components of the actual experimental design process. I mentioned these have been going on for 20 years, and it's been a very static methodology, which is great, right? So if you're doing this over a period of time, you want the same methodology to be followed so that the results are comparable. But it's probably time to start thinking about whether that's still the best way to be doing it. If you do need to make a break in methodology, probably a reasonable time to do that. All right, thanks. Any questions?